Thank you.
And thank you, Kamesh, very much for the introduction. Kamesh, can you indicate that you can see the slides? This webinar series on advanced mobility.
Yes,
you can hear me?
yes.
Okay, very good. All right. Just want to be sure. All right. All right, so thank you. Again, my name is Francis Govers. I'm the Associate Technical Fellow for Autonomy at Bell Textron, and also the founder of the Autonomy Department at Bell. And these days also the chairman of the Textron Autonomy Working Group. So coordinating all the autonomy work across all of the Textron families of companies, include Cessna and Beechcraft, and even EasyGo and our specialized vehicle group, and Pipistrel and our Aviation, which is our electric aviation group. So today we're going to talk about autonomy, artificial intelligence, aerospace, and safety, and how those all can come together, and kind of describe honestly my task and my job at Bell in not just bringing autonomy to our product line and creating, but creating aerospace products that have autonomy as part of their functionality and that incorporate functionality from artificial intelligence in a manner that is first of all safe, reliable, and certifiable, which are all not always exactly the same goal, but certainly for us, we've got to be able to get to the finish line where all of those things are true. So let's start with a quick definition of what is autonomy. And there's certainly a very fine line between an autonomous system and an automated system, and particularly modern aircraft. You've been in an airliner, you know that the aircraft, by and large, quote, flies by itself. In other words, the pilots are not manipulating the controls, they're not turning the wheels and pushing the pedals, and even these days, even moving the throttles. The aircraft is doing all that on its own. What it is not doing, however, is making decisions. It is merely enacting a set of tasks that are programmed into it. If it's given a flight plan, they're going to fly from here to London, England. The aircraft doesn't take part in the decision making. When we go to an autonomous aircraft, now we're talking about the ability of the vehicle to make its own decisions. And to do that, it must understand the environment around the aircraft. The aircraft has to be capable of perceiving, understanding, and reasoning about the environment around the aircraft, and has some understanding also of what its goal is. What is it attempting to do? What is its mission? And so autonomy, the step from automation to autonomy, is a rather big one. And the usual way to tell if a system is autonomous, the easy way to tell if a system is autonomous rather than just automated, is the presence of sensors, the ability of the aircraft to see where it's going in one way or another. This could be electronic means, this could be vision using cameras, it could be LiDAR, 3D perception of the world, a radar, infrared, ultraviolet, multispectral. It's not limited by the physicality as much of the pilot, but rather than the imagination of the engineers and the ability of us to devise different sensors. And of course, we have in that the ability, when we add sensors to the aircraft, the automated sensors have certain advantages. So let's talk first about how autonomy works, and particularly how do we make decisions. Now, decisions are pretty much decisions, whether it's a human making a decision or a computer or piece of software making a decision. The process is pretty much the same. And one of the ways to describe this is not the only way by any means, but one of the ways, the one I like, is called the OODA loop. It was invented originally by Colonel John Boyd of the U.S. Air Force to describe military decision making, and it was intended originally to apply to people. We've since taken this concept and brought it into the autonomy world and used it to describe functionality and software. So in an OODA loop, we have 4 steps, as you notice. Observe, that is to take in the outside environment, to see, perceive the environment around the aircraft, and bring that information into the computer, into the software world. The next step is orient, and honestly, orient is probably the most critical step of the bunch. So if we have, let's say, 10 different sensors on our aircraft, and they're all monitoring the environment in different ways, and they each have their own frame of reference. So if a camera on the front of the aircraft, it sees, things to the right on that image, or to the right of the aircraft, things to the left or on the left. But if we put a camera on the tail pointing backwards, now everything that's on the right-hand side of that image is actually on the left-hand side of the aircraft because it's pointing backwards. So we have to put all of that information into the same orientation, orient the information, put it into the same reference frame. I usually use 2 different reference frames simultaneously to make different kinds of decisions. One of them is the vehicle-centric reference frame, where we reference everything to the center of the aircraft, and all of those references are in polar coordinates, which is to say a distance and a direction from the aircraft. We could say 0 degrees at 2 miles, which would be directly ahead of the aircraft, 2 kilometers away, or 180 at 5 would be behind the aircraft and 5 kilometers away. So this is for decisions, like avoidance, where we're saying, where is this threat relative to the aircraft? Because honestly, none of the rest of the information is relevant when you're trying to avoid running into something. You only care about where it is relative to you. On the other hand, quite a bit of information that we get in, particularly from outside the aircraft, ADSB being the typical component, comes into us in latitudes and longitudes, which is to say that we have to put it on a map. And so we keep a separate tally of information that's in geographic coordinates, or in latitudes, longitudes, or map coordinates. And that's so that we can communicate outside the aircraft. We're going to be talking from our aircraft to another aircraft. We don't, knowing where it is relative to us doesn't tell people as much as it does telling them where it is relative to the map. So we use a map reference frame. We use a vehicle-centric reference frame. We orient all the information. We bring it all into one central place. We call this the Common Awareness Model, or CAM, which is a place where we store all of that information. We need to have it all in one place because when we want to avoid threats, we want to avoid all of the threats, not just some of the threats. And to do that, we need to do that avoidance all in one place. So the Common Awareness Model is where that happens. Next bit is decide. So we brought our information in, we've oriented it, now we need to do something about it. And we generally divide the decide function into 2 pieces. The the 2 parts of it are the analysis of alternatives. So we come up with what can we possibly do. Analysis of alternatives gives us what are the choices that we have. We could go straight, we could turn right, we could turn left, we could go up, we could go down. So from that, we pick from one of those based on some optimization criteria. The optimization criteria I like to use is the risk assessment. So we tend to take not the shortest path, not the cheapest path, not the most direct path, but rather the lowest risk path. What is the path that we can take through the sky that subjects the aircraft to the least amount of risk? And that is the heuristic that we use. And that gives us a way to measure the courses of action and then analysis of alternatives and come up with a course of action that we're going to tell the aircraft what to do. And we have to do that fairly quick because all this is going on in real time and we're really moving through the real sky. And so we have to make a decision before we run into something. So that loop has to run quite fast. So we can't do optimization. We're not looking for the perfect answer in the decide function. We're looking for a good enough answer that satisfies all our criteria as quickly as possible. So instead of doing, if you do a thorough, full optimization, you technically would need to run through, let's say your decision tree has 10 million alternatives. You would have to evaluate all 10 million possibilities of things you could do, even though many of them are very close to one another or physically impossible. But you would have to run through them all and then pick out of that which one is the one optimal solution. And rather than doing that, as soon as we get to a decision that meets all of our criteria, we stop and put out our decision. And then we then send that decision to the flight control system in an aircraft and cause the aircraft to change its course or not, whatever the course of action. The course of action could definitely be keep going the way you're going. The threat's not a concern. But let's say that we decide we're going to turn left. We're going to change the heading of the aircraft. So that gets sent to the flight controls and the aircraft begins to turn. So this loop goes over and over again in the control system. We actually divide our loops into 3 areas: mission systems, completing the overall goal of getting the aircraft to its destination. We have a middle layer that controls the vehicle and is only concerned with flying to the next turn or the next waypoint. And then finally, the inner loop, which is the flight control system that maintains the stability of the aircraft. So there are 3 sets of OODA loops, 3 sets of decision cycles going on, each with that cover different amounts of time. So let's cover some key concepts here and some terms that we're going to carry forward for the rest of the talk. First of all, autonomy is considered a complex system by the FAA and EASA, the European Air Safety Agency. Regardless of whether or not artificial intelligence is concerned, regardless of whether or not it's a deterministic system, autonomy is regarded as a complex system and therefore has a certain set of regulations by the certifying authorities that are separate from other types of systems, simple systems. For example, if you were going to certify an autopilot that all it did was maintain a heading, that's a simple system. But when you add the ability, I'm going to now have an autopilot that not only maintains the heading, but also has the ability to see other objects and avoid them, that's now a complex system. The other bit to know is that autonomy interacts with the environment, which we don't have control over, and it changes. So the environment is as much a part of what goes on in autonomy as what goes on inside the aircraft. What goes on outside the aircraft is equally as important. And you can think of the environment going on. We could have things like we could have icing or rain that covers up the sensor. We could have the sun, sunrise or sunset. The sun's in the lens of the camera. And these sort of things all have to be taken into account. That is, by the way, we generally in autonomy use a principle I call dissimilar redundancy, where if we have more than one, if we want to provide redundancy of our sensors or our sensing capability, we don't use the same we don't say, to have redundancy in case one camera fails, I'll have another camera. Instead of having another camera, I might have a LiDAR or might have a radar that works in a different frequency band, that works in a different modality and sees in a different way so that we have the ability to deal with changes in the environment. So if the sun is in the lens of the camera and then the vision is not working, then the LiDAR is unaffected or the radar is unaffected. And we still can see where we're going. So the environment plays a big role in autonomy, as it should. Of course, to use autonomy on a certified aircraft, that autonomy itself must be certified. And you have to create something called a basis of certification. And there are a number of ways that the FAA and the EASA have put forward to allow certification of complex systems. And we're going to talk about two of them in this talk, along with artificial intelligence. We're going to talk about equivalent level of safety as a concept, and we're going to talk about runtime assurance as a concept. These are ways that we can take complex systems and make them certifiable. So equivalent level of safety is a very simple concept, and particularly for folks like myself, I don't make, or generally we don't build systems that are only unmanned. We build optionally piloted vehicles, OPVs, and those are systems that both can be flown manned or unmanned, or crewed and unmanned. You have somebody on board, you may not have somebody on board. So in that regard, equivalent level of safety means quite simply that the autonomous version of the same vehicle must have the same or better safety performance than the manned version of the same aircraft. So what does that mean in generally? That means in terms of what we talked about in the OODA loop, we need the same level of perception, because we're making decisions. So we have to be able to make decisions as well as a person does. We need the same level of perception, our ability to sense. We need the same level of situational awareness, understanding what's going on around us, the orient part. We have to have the same ability to make proper decisions. And we have to have, quite importantly, the same ability to maneuver the aircraft, which is to say we have to have full authority to maneuver the aircraft to the limits of its capability. So we generally refer to that as full authority flight control. So all of those, so if we can prove step by step that each of those functions are there, we can prove our perception is the same or better. Generally, the aircraft can perceive, the sensors can perceive better than humans can, because we can do things like see in the dark. We can have 360-degree vision. The onboard sensors don't fall asleep. They don't not pay attention. They don't get distracted. So the level of perception should be higher. We have to have the same level of situational awareness. This is actually quite a bit tougher. The same understanding of not just where obstacles and other aircraft are now, but where they're going to be into the future. That ability to predict the results of a course of action is very important. And that comes along with the ability to make decisions. We need to be able to perceive and understand, and then also anticipate what other aircraft or other birds and objects on the ground and so on are going to behave, so that we can make proper decisions. And then finally, the ability to change the course of the aircraft safely is the same. So that's, while it's straightforward set of statements, it is in practice a bit more complex. So I'm going to do a little systems engineering demonstration here. I'm going to take our concept of the OODA loop, and we're going to look at one particular function on the aircraft, which is sensing and avoiding other aircraft. And then we're going to break that down into what is the observed part, the orient part, and so on, and to kind of illustrate what I'm going on about here, and to talk a bit about also how we're going to potentially apply artificial intelligence in this process. So let's start with the function we're going to analyze right now with sensing and avoiding other aircraft. And so we got our 4 steps here, and we're going to spell out what we're going to do in each of these steps in the process of sensing and avoiding other aircraft. So our first bit in the observe, of course, is we need to detect other objects in flight. We can do that with 3-dimensional sensors, LiDAR, radar, and so on. ADS-B, other types of detections, passive and we usually say cooperative and non-cooperative sensors. If the other object is participating in your detection, for example, if they have remote ID, if it's a UAV and it's got remote ID and it's identifying itself, or if it's another aircraft and it's broadcasting on ADS-B, that's a cooperative target, a cooperative detection. And if it's not, if we're a bird, of course, don't require FAA certification for birds, so you have to detect them more passively. So 2D and 3D sensors create our detection. And then, of course, we also have to know where we're at. If we're going to compare, for example, when we take ADS-BN, that comes in the form of latitudes and longitudes. We have to know where we're at in order to understand where somebody else is relative to us. So we have to have our own GPS and inertial measurement units, or to have our own determination of where we are, and also not where we are, but where we're going, our position, our velocity, and our acceleration. So that's the observe part. So in orient part, so we combine the data into what we also call this the COP. This is I guess an earlier version. COP stands for Common Operating Picture. We've since started calling it Common Awareness Model, because there's another COP, Common Operating Picture, elsewhere in the aircraft that we don't want to get confused with. But you can still call it a COP or a CAM. We first have to eliminate duplicate data, which is to correlate data. So that is, if we have 4 sensor detections with 4 different sensors, it can be extremely difficult to tell if we are seeing 4 objects once each in each sensor, or are we seeing the same object 4 different times with 4 different sensors. It could be that we have enough overlapping field of view that there's only one object there, but we've sensed it with 4 different sensors. In fact, that would be far preferable, that we are seeing things across different sensors, and therefore we have to correlate the movement of the objects in the perception. Where is it? What does it look like? What is its signature? And correlate that information to determine if we are seeing 1 object or 4 objects. We of course have then to figure out where they are in distance, and then also at all points we have to propagate all of our information into the same time frame. Since we get information at different rates, ADS-B being kind of the poster child for this, and that we only get an ADS-B data in once a second. So, but we're getting in our camera and LiDAR and radar 20 times a second. And we're updating our position estimates at 100 times a second. So if we're going to be making decisions in those kind of time frames, we have to get everything into the same time slot. And so we have to propagate, or we use the term coast occasionally, the data that we get into the same time frame, so that we're comparing where we're at now with where we think the objects are now, so that we can do our decision making. So this propagating everything into the same time frame is a very critical function. The next bit is decide. Now we've got to determine a few things. We've got to first determine is there a risk of collision. I generally do this by doing a 4-dimensional volume around my aircraft, and then a 4-dimensional volume around all the other aircraft that I can see, and projecting them forward in time. And so a 4-dimensional volume has an XYZ shape, and then it moves forward through time. So that's our 4th dimension. We actually create a volume in 4 dimensions mathematically. These are mathematical 4 dimensions, not actual, well, I guess they are actual 4 dimensions. But one of those dimensions being time, and we can then do a fairly simple calculation to do the 2 volumes intersect. And if they do, then we know that there's a risk of collision. And we add some safety buffer around, of course, our aircraft and the other aircraft. And then we have to determine where the risk vectors are. That's my term for which direction is the threat coming from. Where is the threat in space, and where is it going, so that we can then do the next part, which is our analysis of alternatives. I mentioned before, let's figure out, okay, now we know where it's coming from, what are we going to do about it? And then finally, from that, we pick some optimal course of action. As I said, our heuristic is risk. And then once we've done that, we now have a new path for the aircraft to follow. We send that new path to flight control. We then have to monitor that the flight control is actually doing what we wanted it to do, that it's it's executing the maneuver we asked for. And under that, we also have 2 other functions going on that are kind of independent. They run all the time. And one is called envelope protection, which is just the part of the control system that monitors that we have not exceeded any of the limits that we've set on the aircraft, that we haven't turned too hard, or we haven't pulled too many G's, or we haven't exerted the flight controls in a direction that they're not designed to go in. The envelope protection watches over the control execution and makes sure we don't do anything that could harm the aircraft. And then runtime assurance is a separate system that's monitoring the, let's say, the data quality or the data integrity of the information coming out of the autonomy system, and watching to see that the autonomy system is producing consistent results. And if it sees that it's not, then it will clamp down on the autonomy and actually drops to a lower level of automation temporarily to keep the aircraft in line. So this runtime assurance, we call the deterministic safety net, underneath the autonomy that monitors autonomy and makes sure that it's operating in a proper fashion. So from there, let's talk a little bit more about perception. So perception can be divided into different tasks, and I've got 3 of them here. There's we detect, which is determining whether or not there's something there. So you look out into the environment, and either there's something there or there's not. If there's something there, you have a detection. If there's not, of course, you don't have a detection. Now, you may have, in all of these, we may have false positives, which is to say we think there's something there when there's not. And we may have false negatives, where we say there is not something there and there is. As you can probably understand, we're far more concerned with the false negatives than the false positives, because what happens if you have a false positive and you react and you avoid an object that's not there? And the answer is generally nothing. You just make a course change that you didn't need, but you've gotten into no danger. What happens though if you don't avoid an object that really is there? Now you're going to collide with it, and that's a much more that has far more consequences. So we really watch our false negatives far more closely than the false positives. But we certainly don't want false positives to be an annoyance. So our detection area. Next one is classify. Figure out what kind of an object it is. I've deliberately fuzzed up these objects here, so you may have a hard time figuring out which is which. And then finally, identify is to track objects individually. So when we say identify in the perception field, we want to, if we have 3 airplanes, we want to, when we're tracking them, we want to keep track of the same aircraft consistently so that we can predict where it's going to go next. And if we mix up which aircraft is which, you can mix up their tracks as well and their data and end up with an inconsistent track. So identifying the object individually, this bit about do I have 1 object or 4 objects, is quite important. So in this case, for our perception, you can see this is what we actually saw. All stuff from Bell, helicopter, and some objects you may not have seen before. UAVs these days are in all shapes and sizes. You can see the apt here, which is a quad rotor biplane. And then Bell is also famous for the jetpack, which we invented back in the 60s. So who knows well, actually jetpacks are making a comeback these days. So you got to figure out what it is that you're seeing, and then and understand that each of these functions, detect, classify, and identify, happen at specific ranges and resolutions of your sensors. So you can detect an object much farther away than you can classify it, and you can classify an object farther away than you can identify it. So each of these comes with its own limitations, because it takes more. We need increasingly more information at each of these levels. So the next bit is data fusion. That's bringing all that data together and putting it into some sort of information. You can see, the cockpit of a helicopter can be a very busy place, and there's a lot of stuff going on in this picture. We've got a helicopter that's making an approach. It's banked. The pilot is looking out of the window, as well as at the instrumentation that's on the control panel in front of them. They've got a moving map. They've got an attitude display. There's a lot going on out there. They're coming into an airport. There may be other aircraft in the air around them. And all that information has to be brought together and processed in the mind of the pilot, or in our case, in the mind of the software that's running the autonomy. So that data fusion function is quite important. So our next bit in our decision is doing an analysis of alternatives to create a course of action. There are a number of ways of doing that. What the illustration I have here is a decision tree where we have some series of nodes that are connected via links. Each of those links has a cost or a heuristic attached to it. It may be distance, it may be speed, it may be, like I said, in my case, it's generally risk that we add to that. And this stepping through this decision tree brings us to some analysis of a course of action. So you can see in this particular case, the yellow arrows, the green is the possibilities. This is all the potential courses of actions we could take. And you can see they may have multiple steps involved, not just one step at a time, but multiple steps at a time down this decision tree. And that some combination of moves, in this case, we've got these 5 moves that we've determined are the best to get us from point A to point B, or in this case, point 1 to point 15. So this decision functionality could be simple as this decision tree type technique shows, deterministic, or it could be very complex. We could have an artificial intelligence involved in this. This could be a learned function that we have trained, but it's still the idea is that we come up, given the information, come up with a way to deal with what's going on. And then final bit is the control. This is a sample of flight control system using PID controller, proportional integral derivative, to maintain a particular control, and it could be altitude, airspeed, heading is generally the world we live in. We control the aircraft by changing its altitude, airspeed, and heading. And those are maintained using some sort of mathematical function like this PID controller. So, so the next bit is in our process of, we talked about, back previously about how do we go about proving in our equivalent level of safety, how do we go about demonstrating or showing that a system is safe? And this, again, fits into any type of system, complex, simple or complex, And I've come up with this particular technique that originally was designed to do verification and validation for the F-35 Joint Strike Fighter, but we've since used it successfully in a number of different fields. And that's to ask a series of questions about what the system is doing, and then use those answers to derive our validation techniques or our certification process. And so we first ask, who is doing what? So who is the autonomy system? What are they doing? They're detecting other aircraft. We're still talking about our detection function here. We're detecting other aircraft and other objects. When are we doing this? We're doing this anytime we're flying, but we're in flight. So we're in the air at day or night. And by definition, in VFR conditions, because if you're in IFR conditions, you can't see. So so during VFR conditions, use when you do detect and avoid. Where are you doing it? You're doing wherever the aircraft flies. Let's say in this particular aircraft, it only flies up to 12,000 feet. And then we can say, how much do we do horizontally? If we did the equivalent level of safety, what we would say, what is the pilot able to see? And we'd say, well, the pilot can see 140 degrees horizontally, 60 degree, or 140 degrees plus or minus 60 horizontally, plus or minus 30 degrees vertically through the windows. That we may give for the autonomous system a field of view of 360 degrees with vertically and horizontally, ideally our 4 pi steradian ability to see, which typically how this is specified. And then the next one is probably, to me, the most important part of it, which is why are we doing it? Well, we're doing this to avoid a collision. And why do we want to avoid a collision? Because a collision could result in damage or death. That is very important. So that means that this is a safety critical function. And so that informs the next part, which is how well do we need to do it? Of course, we need to be able to do it with enough time to be able to maneuver to avoid a collision and fit into the OODA loop, observe, orient, decide, and act. Then we have to figure out how often are we doing this? We're doing this continuously during the flight. And we need to cover our, in this case, I said, we need to cover our entire field of regard, all 360 degrees every 2 seconds. And in order to be successful, and then how much traffic do we need to consider? Now, I looked around and said, what would be the most traffic you would ever see in the immediate vicinity of an aircraft all at one time? And the answer to that generally is Oshkosh, which is an air show that happens every year in July up in Oshkosh, Wisconsin. It's the annual conference of the Experimental Aircraft Association. It's the largest air show in the world. And they generally have 400,000 people attend this show. And they generally have 70,000 something aircraft attend. And it's traditionally the highest density air traffic control event in the world ever. So you could say Oshkosh is an upper limit, and then some other typical traffic load might be, so let's say 10 aircraft in the field of view at a time. But you got to pick your level of capability. So let's talk about in how we then incorporate. So let's go back a little bit to our OODA loop. I'm going to jump backwards a little bit. And in this functionality that we've got, we're looking for other aircraft, and we're going through these steps. Where would we apply AI, artificial intelligence, in this process? So, and the answer is generally in the observe part, in perception, and then mostly in the ability to classify objects. So we said we were going to do detect, identify, classify. Detect, classify, identify, sorry. So in the classification is what kind of an object is it? Is it a bird? Is it a plane? Is it Superman? In that functionality, that's maybe a very good use for artificial intelligence. It is kind of important to note that in that one, the criticality of getting the classification right is not as high as it is in detection or in tracking. That we do have, if we say, oh, that's a plane and not a bird, but we've still got the tracking right, we've still got the speed right, the altitude right, and the heading right, but we've misidentified it, is not as critical as if we didn't know where it was. So so this is a lower level of criticality, but still a function, let's say, that makes decision making better rather than it's not making the critical part of the decision, but it's making that decision better. So you can use artificial intelligence in that function. The next bit, in the orient step, would we use artificial intelligence for this? Probably not, in that these functions, this combining the data and eliminating duplicates, is a pretty much a mathematical function and deterministic and doesn't require help. But in the decide function, this doing an analysis of alternatives, that is very much the world of decision trees. And course of action analysis is very much a world where AI can be used. You could use a neural network that's trained on avoidance maneuvers, or you could use a predictive function to say this is the most likely place for objects to be, or to be how they're going to behave in the future, and use that trained function to compute analysis of alternatives. It's important at the end, though, that you have some ability to validate that course of action, that it's the resulting course of action is safe, and that should be separate from using AI to do analysis of alternatives. So those are functions that we could very possibly use in artificial intelligence. We're actually talking right now with inside the aviation community and with folks like Dr. Namaduri about what we're going to do with these large language models, the chat GPTs and other types of llamas, large language models that are out there. And one of the interesting functions that they could possibly do is to read technical manuals or to digest technical manuals and then potentially assist the pilot in this kind of digital co-pilot world of assessing what a potential course of action would be given a particular set of events. So if you have, for example, a certain instrument indications that may show that one of the engines is about to fail, that you could potentially talk to a large language model and have it diagnose the symptoms that are currently going on, and then just suggest, based on the consumption of the technical manuals, what the problem could possibly be. Oh, these set of symptoms match oil failure in the turbine intercooler, and therefore in the next 2 or 3 minutes you're probably going to have your turbocharger fail, and you need to do something about that, reduce your power or whatever. So we're very excited about those as potentials. We still have to decide how we're going to validate the data and how we're going to validate the semantic models in such a way that we can understand that the data that we're getting out of them is reliable. And that is work that remains to be done, but we're quite excited about the prospects of doing far more reasoning-based implementations of AI than just the simple neural networks. So let's go down here to this diagram and talk about this. So this was created by a company called Dedalian. They happen to be friends of mine. Luke Van Dyke, who's the CEO, gave me permission to use this diagram in this presentation. And they have come up with a verification methodology. We talked previously about verification and validation. So they've come up with a verification and validation methodology that includes artificial intelligence. And they have succeeded in convincing and through a lot of hard work, through organizations like IEEE, to implement this as a formal verification methodology. And that adds to the typical way we would do verification, which is a V-shaped diagram with this W. And you can see in the bit is this learning process verification. Though it says that if you're going to use a model and you're going to train it on data of some kind, I just mentioned, using technical manuals to train an AI how to make decisions about how the engine's performing, that data itself needs to be verified. And that data itself needs to have the same level of configuration management that everything else in the aircraft has. And so it adds the data, since typically how an AI works is that it's the data that determines the behavior of the system rather than the neural network. It's the programming. The programming says, here's a neural network. We're going to make decisions with it. And then it's based on the data that's used to train the neural network on how it's actually what kind of answer it's going to give you. And so that data needs to be as much a part of the verification and validation of the process as the software is. In fact, more so. The data is far more important than the software is. As I could probably configure a neural network 10 different ways. If I trained it on the same data, I would probably come up with a fairly similar result. And it would just be a question of what the distribution of error would look like. So this technique, as I said, which we call generally the W diagram, that Dedalian came up with, is one basis of certification right now that AI can be used in aircraft to show safety. And this is in the process, I guess, of working its way through. It's been proposed by the EASA as a basis of certification. It's been transferred over to the FAA. The FAA is now currently looking at it as well. And it remains to be proven through the process of actually implementing it and seeing if it does what is claimed to create safe, certifiable AI system. So with that, I'm going to go ahead and finish up since I'm out of my time here, and I definitely wanted to leave time for questions. I wanted to say also thanks to the IEEE Vehicle Technology Society for their sponsorship of this series and for their kind invitation to have me come talk today. And Dr. Namaduri's coordinated all of this between the speakers that he's going to be presenting over the next few months. And with that, I will stop sharing and let's talk about questions.
Yeah. First of all, thank you, Francis, for the. Sorry, thank you, Francis, for the wonderful presentation. I will wait for others to ask questions. Otherwise, I have one question from you. If there is some echo coming, please, if someone has their mic open, please close.
Yeah, go ahead, Kamesh.
Yeah, Francis, actually, there may be something on the chat, so please keep an eye. But yeah, my just a question is, as we work towards this autonomy and intelligence, that we need to we'll be also looking at the capabilities of the vehicle itself. So how do we trade off between how much we need to do on board and how much we need to depend on the ground control station towards the autonomy? So would you please elaborate a little bit on that?
I'd be delighted to. Yeah, that's definitely a subject that we've been quite excited about, and groups like the GAMA, General Aviation Manufacturers Association, and RTCA and ASTM have also been involved in this and trying to figure out what it's like, because there certainly is an ability to do some of the processing on the ground. In fact, a lot of the way air traffic control works today is that the ground controller have most of the information, and they're relaying that to the aircraft that are in the air via radio, which is an imperfect means of doing that. But I personally feel that as much needs. So the advantage of doing decisions on board is you're there, you're very close to the data, and anyone who's on the ground processing data, of course, is a bit more removed. So we feel that in terms of eventually, where we would like to end up with is doing as much processing on board, and honestly to relieve as much of the air traffic control burden from people like the PSUs and the air traffic control authorities by letting the aircraft talk to each other electronically and generating their own course of actions between them, so that let's say 99% of the cases can be resolved that way. And then we just have a few small exceptions that need to be handled by the air traffic authority. And that makes the whole thing scalable.
Yes, yeah. Thank you, Francis. The audience are, feel free to ask a question if you haven't, either on the chat messages or directly. The other thing that I have in mind is in terms of this autonomy levels, like there are levels of autonomy that are defined in general, but do we have such levels defined specifically for unmanned aircraft?
There are a couple of versions. The SAE, Society of Automotive Engineers, has their 5-level version. I have developed one we use at Bell that also has 5 levels, but they're slightly different. But yeah, there's a few different versions of that that are around. I think the Army and the Navy each have come up with their different versions. The Army, just recently kind of surprised us by reinventing several of the terms for autonomy. They came up with something called unsupervised autonomy, which we would previously have thought meant unsupervised would mean autonomy that doesn't require somebody on board. But they took it to mean a system that doesn't have a command and control link at all, which has no telemetry, has no outside interfaces, which was an entirely different level of autonomy than we had conceived. So those are still kind of evolving, and it's kind of interesting that where people are pushing the boundaries of autonomy. Where I talked about we generally talk about pilot assistance systems that are just provide information, and then we have digital co-pilots that do some of the directing and make some of the simple decisions or provide advice, and can do simple functions, and then simplified vehicle operations where some of the controls are made easier. For example, hovering, or for a helicopter, if we have an automatic hover, that's a SVO, simplified vehicle operation function, where we're trying to take the physical skills out of being a pilot and putting it into the aircraft, which I think for helicopters especially is quite important. And then the next level up is supervised autonomy, where you have a pilot on board, but they're not directing the aircraft. They're just there for safety. And then finally, the unsupervised autonomy, where there's nobody on board.
Yeah. Thank you, Francis. I don't see any questions on the chat, but if anyone has any question, please feel free to unmute and go for it. We'll wait for a couple of minutes. But in the meantime, I would like to thank Francis for a wonderful presentation, and this is the webinar series is going to continue. We have speakers lined up until March or April 2024, and occasionally you will also see more than one seminar or one webinar per month. These are based on some related and ongoing activities, and depending on their relevance and importance, we may have more than one, but that is exceptional, not a norm. So if there are no questions, then I welcome again everyone for the next seminar. So please keep an eye on the announcements, and then see you next month. Yeah. Thank you, Francis. I think
thanks, Kamesh, for all your help with this, and I hope you enjoyed the talk.